Hello and welcome to the chapter 15.8 lecture on Lagrange multipliers. So in the previous section, we encountered a maximization-minimization problem subject to constraints. So for example, maximizing or minimizing this function within the unit disk, x squared plus y squared was less than or equal to 1. That involved finding the min or max along the boundary and solving for the min or max of this along the boundary involved parameterizing this curve. And we can do that by, well, solving for y. Y is the square root of 1 minus x squared and plugging that back in. Or we could do a sine theta, cosine theta parameterization. Either way, it's a mess or impossible for certain relational constraints in which it's not possible to solve for y in terms of x. And at best, it's a mess in most cases. And Lagrange multipliers are a clever way to solve min-max problems subject to constraints, which avoid the necessity and sometimes impossibility of parameterizing the constraint. Okay, before we begin, we need some terminology though, just two pieces. The objective function is the function that we wish to maximize or minimize relative to the constraint. So for example, if we were given the problem, find the absolute minimum of z equals this function along the circle x squared plus y squared equals 1, then this guy would be the objective function, while this guy would be the constraint. Yes, we always minimize or maximize the objective function relative to the constraint. And for the purpose of Lagrange multipliers, which we are about to learn, we will always wish to express our objective function in the form f of xy and our constraint function in the form g of xy equals 0. So, for example, over here, we would wish to express that as x squared plus y squared minus 1 equals 0, which is just a rearrangement. And then this would be of the form g of xy equals 0. So to get into that form, we just always move everything to the left side and make it equal to 0, and that's it. And one of the reasons that we'll be doing that, the reason actually, is to think of the constraint as the level curve of a higher dimensional function. We customarily call the constraint curve just c. Okay, so for example, if we wanted to maximize z equals this guy along the line y equals x, what would be our f and g? Well, we want to maximize this. That's our f. And then our g, we would take this and move everything to one side. Okay, now this guy is our g. This is our g of xy equals 0. That is our desired form of g. Yeah, so the reason that we wish to express the constraint in the form g of xy equals 0 is to think of it as a level curve of the function g of xy. Okay, and to recall that the gradient of f is always orthogonal to its level curves and points in the direction of steepest upward slope. So this is the picture from then. Here's a paraboloid, and we have its level curves, and the gradient is always facing orthogonal to the level curves of that function and pointing in the direction of steepest upward slope. And it's always orthogonal to the level curve because the level curve is pointing in the direction at that point that is no increase or decrease. So here's the core idea behind Lagrange multipliers. It's very clever. So we know that grad f is always orthogonal to its level curves and points in the direction of steepest upward slope. So that means that wherever the gradient of f is not orthogonal to the constraint curve c, so at this point, for example, then that means that there would be some component of f that is parallel to c, doing an orthogonal decomposition like this. And then if we move in that direction, then that means that f is increasing, since the green is the direction of steepest upward slope of f. And if it's not orthogonal to the constraint curve, then we can do that orthogonal decomposition by projecting it onto the tangent vector to the constraint curve. And that is a direction we can move in which we're increasing. Just look at the level curves here of f. Here's of f is of height 1, height 2, height 3, etc. Okay, so that's the case wherever we're not orthogonal. And where we are orthogonal to the gradient of g, then that means that we're orthogonal to the constraint curve. And that indicates that a movement to the left or right would not increase or decrease the value of the function of f, and therefore this must be a local minimum or maximum, or possibly a one-dimensional saddle point in the same way that the cubic is. So in other words, all mins or maxes of the function subject to the constraint must occur where the gradient of f is parallel to the gradient of g, so that our picture looks like this, and this is not the case. And that parallelity is where one is a scalar multiple of the other, so the gradient of f is lambda times the gradient of g. This lambda is our Lagrange multiplier, and we can solve for the maxima or minima of f subject to a constraint by just setting up this equation, essentially, and solving for the values. So here is our process. Given an objective function f and a constraint g, and the usual differentiability conditions, then to locate the absolute minima and maxima of f subject to the constraint, carry out the following steps. We find all values of x, y, and lambda that satisfy the equations grad f is lambda times grad g, so that we're at a point like this, where it is going to be a possible local minimum or maximum. And then we evaluate, and we also need to have, of course, that we lie on the constraint itself. And then we evaluate the function at those various points and find where it's minimized or maximized along that constraint. So let's do an example. Let's find the maxima and minima of x squared plus y squared plus 2 subject to this constraint. Okay, so notice this constraint here. If we were to solve for y in it, then we would have to use a quadratic formula because we have a y squared and a y, likewise with x. So solving for y or x and then to substitute back in would be horrific. We do not want to do that. This is a problem that would be horrific to do just about any way except Lagrange multipliers. And here's a picture of what's going on. So it turns out that this constraint is an ellipse whose major axis is diagonal to the x and y. And we want to minimize or maximize this paraboloid along or above this ellipse. And you can see that this would have two minima there and there and two maxima there and there. Okay, but how would we do this from scratch? Oh, and let's take a look at this picture. So this can help you see geometrically that the minima and maxima occur where the level curves of the objective function are parallel to the constraint curve. Where they're not parallel, then moving along the constraint curve in some way would increase or decrease the altitude. That's the idea behind the Lagrange multipliers. Okay, so let's go through how to do this algebraically. So first, we need to identify our f and g. This is our g of xy. It's already in the form g of xy equals 0, and we have our f. Okay, so what do we want? We want grad f to be lambda times grad g, and we want to lie on our constraint curve, g of xy is 0. Okay, this first equation, what is the gradient of f? That is 2x, 2y, and that must be equal to lambda times the gradient of g. Gradient of g is 2x plus y, comma 2y plus x. We're just computing the partial derivatives of this f and that g. Okay, and we need to actually lie along g, so and x squared plus xy plus y squared minus 4 is 0. Okay, now what we can do is realize that this is a system of equations. We can distribute the lambda to both parts. And if two vectors are equal, their components are equal. So from that, we get that 2x is lambda times 2x plus y. And also 2y is lambda times 2y plus x. Okay, and then this guy is still hanging out. And we have that we must lie along the constraint curve itself. So we end up with a system, and we want to solve this system for x and y. Now, this might look intimidating, but it really isn't that bad, because something will always happen that's very nice, and that is to eliminate lambda, you just divide one equation by the other, and lambda over lambda goes away, and it just always works out really nicely. Okay, so what we had was this system of three equations, And lambda always cancels out very nicely. We can always do the following thing, and I would highly encourage you to always do the following thing, which is just divide one by the other. So dividing one by the other, we have 2x over 2y is lambda 2x plus y, etc. And lambda over lambda goes away. And by the way, we do not care about the value of lambda one bit. We only care about what the actual x and y are at the minima or maxima. Okay, so then we have from this cross multiplying 2x times 2y plus x is equal to 2y times 2x plus y. And that's 4xy plus 2x squared is 4xy plus 2y squared. And once again, we have a very nice canceling of things. We wind up with just x squared is y squared, aka y is plus or minus x. Okay, so the first two equations reduced to y is plus or minus x. That's super nice. Now we can deal with this last one. By the way, this general order of how to do it is what I would always recommend doing. First, you would divide to eliminate the lambda. Don't worry about the constraint at all until after you deal with the first two and get a nice relationship between x and y. And only then do you worry about the constraint and plug in. So at this point, we can plug into that constraint now that we have this simple relationship between x and y. Okay, but how should we do this? We have y is plus or minus x. So let's do it case-wise. It's the easiest way to not confuse ourselves, and this type of situation will happen a lot. Okay, so we got that y is plus or minus x. That is what the first two equations of our Lagrange multiplier is reduced to. And now we need to deal with the fact that we're also on the constraint curve. That is the last constraint in our system of equations. And that constraint curve is just this, we're given it. So the way to best do that is to break it down into cases depending upon sign. So case one, that is when y is equal to x. When y is equal to x, then that means that we have x squared plus x times x plus x squared is 4. And that becomes 3x squared is 4, or x is equal to plus or minus the square root of 4/3, aka 2 root 3 over 3. Okay, and case 2 is when y is equal to negative x. Okay, in that case, plugging in, we have x squared plus x times negative x plus negative x squared is 4. Negative x squared is positive x. And we have that x squared is equal to 4, so x is plus or minus 2. And for each of these, we should also list the y values. After all, what we want are entire coordinate points. So here, y was x. So when we wound up with getting that x is that, then what we really have are the two coordinates, 2 root 3 over 3, comma 2 root 3 over 3, and negative 2 root 3 over 3, comma negative 2 root 3 over 3. Because in this case, y was x. So whatever x is, then y is that same thing. Okay, on the other hand, for x equals plus or minus 2 in this case, y was negative x. So we have our x values of 2 and negative 2, and then the y values for each of those swaps the sign. Okay, so we have now found all points along the constraint curve where we might have a minimum or maximum. And now at this point, we make a list, a table of all 4 and their outputs, and just find wherever it's minimized or maximized. So we found these 4 points. And now what we do is we make a table and just plug each of these points into our f. Each of these points is one of our candidates for the minimum or maximum of f subject to this constraint. And plugging this into f, we would have, okay, for the first point, we have 4 times 3 over 9 plus 4 times 3 over 9 plus 2 is 14 over 3. And similarly, this point also achieves 14 over 3. At 2 comma negative 2, plugging in, we have 4 plus 4 plus 2 And similarly here, we have 4 plus 4 plus 2. Okay, now, which of these guys is the biggest versus smallest? Clearly, 10 is larger than 14 over 3. So these guys, this is where the maximum occurs. Either of them, they're both absolute maxima. And these are where the minima occur. So in conclusion, we would write that we have maxima of f equals 10 at 2 comma minus 2 and minus 2 comma 2. And we have minima of f equals 14 thirds at 2 root 3 over 3 comma 2 root 3 over 3 and the negative of that. So that concludes this problem. We have found the minimum and maxima of this. And let's go back to the picture just to see if that makes sense. Okay, so we got these maxima of z equals 10. That's exactly what we found at 2 comma negative 2 and negative 2 comma 2. And then at these 2 points, we got minima of z equals 14 thirds. That is exactly what we got. So checks out. Okay, I encourage you to pause the video and try your hand at finding the maxima of this plane above the unit circle. At what value is it maximized? Okay, so we want the gradient of f to be lambda times grad g, and we want gradient of g to be 0. Okay, so first, this guy, we need to rearrange that as x squared plus y squared minus 1 equals 0. And now this is our g of xy, because we always need our g of xy to be equal to 0. And our f, though, is fine as is. So that and g of xy, we just lie on our constraint curve, is 0. Okay, so what is the gradient of f? That would be 1 comma 2 equals lambda times the gradient of g, that would be 2x 2y. Okay, so what do we wind up with? Well, distributing this lambda and setting the components equal, we have 1 is lambda times 2x, 2 is lambda times 2y, and we have that x squared plus y squared is 1. Okay, and we do our usual thing of dividing one by the other. We have 1/2 is lambda times 2x over lambda times 2y. Those go away. We don't even care about them. They're good dummy variables really. And we have 2y is 2 times 2x, and that implies that y is 2x. Good. So we have found that y is 2x. From the first two equations here, we'll always get some nice, hopefully nice relationship that we can then use to plug in to our constraint and solve for the value or values of x and y. Okay, so we got that y is 2x, and we still need to deal with the fact that we're lying on our constraint curve. Okay, so plugging in y is 2x, we have that x squared plus 2x squared is 1. That means that 5x squared is 1. So x is plus or minus root 5 over 5, solving for x there. And then since y is 2x, y is plus or minus 2 root 5 over 5. Okay, so we get our two candidates for minimum and maximum. Those are root 5 over 5, comma 2 root 5 over 5, and negative root 5 over 5, comma negative 2 root 5 over 5. So those are our candidates for the minimum and maximum of this function above this circle. So now it's a matter of just plugging in these 2 points into this and finding where is it maximized. Okay, so we got our 2 candidate points, and now we just plug these back into our f and see what happens. Okay, so at this first candidate point, we get 3 root 5 over 5, and over here, we get negative 3 root 5 over 5. So we therefore have found our maximum and minimum. the problem was asking where is it maximized, and we would say that it is maximized subject to this constraint at the point root 5 over 5 comma 2 root 5 over 5, at which point f achieves a value of 3 root 5 over 5 is its maximum value along that constraint. And the same idea applies to 3 or more variables. It's exactly the same. It's just that now your algebra might be a bit more complicated, but it's all the same idea. And let's conclude this lecture with an example of a Lagrange maximization where we have 3 variables rather than 2. And this one is straight from the homework. Suppose that a delivery company requires any box delivered must have length plus girth, where girth is the distance around, totaling no more than 144 inches. Find the dimensions of the box with the maximum volume that can be sent. Okay, so first let's be clear on what we mean by the girth. So we have this box, say with dimensions x, y, and z. The girth is the distance around, so it'd be x plus y going all the way around. That's 2x plus 2y. And then we have our length, which is z. And we want to maximize the volume. The volume is, of course, x, y, z. And subject to the constraint that the length plus the girth, which is 2x plus 2y, must be no more than 144. Okay, well, it is going to clearly be maxed when it's exactly equal to 144. So we want to maximize v as x, y, z, subject to z plus 2x plus 2y is equal to 144. Okay, so now let's begin. First thing, we want to get this constraint into the form something equals 0. And our problem becomes this. We want to maximize this objective function subject to this constraint, and we express it in the form g of xy equals 0. Okay, so first, we want grad f to be lambda grad g. Okay, that would be yz, xz, xy is equal to lambda times 2, 2, 1. And distributing that out, we have the system. Okay, yz is 2 lambda, xz is 2 lambda, and xy is lambda. Okay, and we still have our constraint naturally. Okay, and once again, we have a not very pretty system. I mean, it's 4 variables, 4 equations. However, we can always cancel out lambda. And in the 3 variable case, probably the slickest way to do that is to divide pairwise. So to be clear, do pairwise divisions. So for example, this blue here means that we'll take yz over xz equals 2 lambda over 2 lambda. Yz over xz is y over x, these cancel out, and 2 lambda over 2 lambda is 1. Okay, and the green, that means you're taking yz over xz, which is z over x. That is 2 lambda over lambda is 2. And this purple, that's xz over xy, is z over y, is 2 lambda over lambda is 2. Okay, and from these, we get a nicer, simpler set of relations. Okay, so the first guy just says that y is x. How pleasant. Second guy says that z is 2x. Third guy says that, okay, well, if y is x, then z should also be 2y, and that's exactly what it says. Okay, and now that we know that y is x and z is 2x, we can just do a simple substitution in here to get x, for example. So this would now be 2x plus 2x plus 2x is equal to 144. Because 2x, that was our z, this was our y, as we found. So the simple substitution from what we found yields that. Okay, so from that, we have 6x is 144, so x is 24. And then also the fact that y is x means that y is 24, and then z is 2 times x, so z is 48. And that's the answer. So that's the dimensions of the box that satisfying that constraint with the maximum volume. All right, that concludes Lagrange multipliers and also concludes chapter 15 as a whole. Have a great one.